Good morning, everyone. It's Miss Butler here. We got some notes today on isotopes. So first goal, we got to be able to define isotopes. What are they? How do I know? I want you to be able to identify isotopes and write the isotope name and symbol, two separate things. And then calculating the average atomic mass of an isotope is where we will spend most of our time in this video. Just a little review in case it's been a while or you were gone from class. We have three subatomic particles that we are focusing on this unit. The first are called protons, and the protons tells us the type of atom. Every element on the periodic table has an atomic number. That is the number of protons. So oxygen always has 8 protons, the atomic number 8. As soon as I add another proton, now I have 9 protons. That's going to change the element. It's now fluorine. So number of protons tells us the type of atom. The number of electrons will tell us how an atom will behave in a chemical reaction. And remember, the number of protons minus the number of electrons equals the charge of the ion. So really messing with the number of electrons is going to create an ion. Remember, ions are atoms with a charge. And last but not least, neutrons will change the isotope, and neutrons determine the mass number. Protons plus neutrons equals the mass number. So by changing the number of neutrons, you are changing the mass number of the atom. So let's get into that first goal and being able to define isotopes. Isotopes are atoms with the same element, but they have different numbers of neutrons. So when I say same element, I mean the same number of protons or same atomic number, right? Those are going to be the same exact thing. But the neutrons are going to be different. What does that mean? They have a different mass number, right? So the only way we can tell isotopes apart, a carbon-12 isotope from a carbon-13 isotope, is by their mass number. Actually, if I had a handful of carbon, so I have a bunch of carbon atoms in the palm of my hand, okay? And I know you can't see me right now, but I want you to hold your hands up like you're begging for something. Picture a bunch of black little particles in there, kind of like the lead on your pencil. That's graphite, that's carbon. If I had a bunch of carbon atoms, it's actually a mixture of a bunch of different carbon isotopes. So still 6 protons, all carbon, but each little atom is not guaranteed to have the same mass as the atom next to it. Could I piece by piece pick apart carbon-12 from carbon-13? No, because isotopes are going to look the same, they're going to act the same in a chemical reaction. They will not behave differently in chemical reactions because chemical reactions only involve electrons, and for isotopes, the electrons aren't different. Isotopes will act differently in nuclear chemistry, which we will study later this unit. Because nuclear reactions involve the nucleus, and what's different about isotopes? The number of neutrons in the nucleus. All right, so first thing first, here's how we write isotope symbols. We put the element symbol, so Cu is copper. So that's just regular from the periodic table, one uppercase letter or an uppercase letter and a lowercase letter. We put the atomic number down here. So this is the atomic number. So bottom left. That's also the number of protons. And then in the upper left corner, I gotta do my L's and my R's. My upper left corner, we have the mass number. And remember, mass number is the protons plus the neutrons. All right, next we have the isotope name. The isotope name is different than the symbol. We're gonna put the full element name, so carbon, right? Spell out the whole name as it's written on your periodic table. And then we put a little dash and then the mass number. So notice the isotope name does not contain the atomic number, just the mass number. And remember, mass number, protons plus neutrons. So I want you to pause the video and practice. I'm giving you 3 isotopes of argon, 1, 2, and here's the third one. I gave you the isotope name. Notice it says argon-36, argon-38, argon-40. I want you to write the symbols. That's, remember, X, Y, A, right? We'll do AR since we know it's argon. So fill in these numbers for me for the 3 isotopes of argon. Okay, for real, pause the video. No, really, pause the video. All right, we're going to toss those guys in there. So we have argon. And we know this is the mass number, right? So mass number goes up top. I'm going to do that for each one, argon 38 and argon 40. And then I'm looking at my periodic table, I find argon. It has the atomic number 18, which means it has 18 protons. So all of these have 18 down here. So what's interesting, all of these are argon. None is the actual argon, right? All of these combined together make argon. If I had a handful of argon, that would be kind of difficult to do, but just work with me here. If I had a whole sample of argon, it is a mixture of these different isotopes of argons. They're all argon because they have 18 protons, but they have different mass numbers, different numbers of neutrons. All right. I'm going to need you to really bear with me here because this is where chemists like to confuse each other and confuse ourselves sometimes because we just pick all of these words that sound so similar. So there is a big difference between all of these things on this page. So I want you to really focus with me because we need to know the difference. So the first is mass number. When I'm talking about mass number, I'm talking about one specific atom, and I'm taking the number of protons plus the number of neutrons. This is what we've been doing in class all week long. So number of protons, number of neutrons, it's always going to be a whole number because if I am an atom, I can't have 0.3 neutrons. It's just not possible. So mass number is when we're looking at an atom, how many protons, how many neutrons. The atomic mass is experimentally determined, and we're finding the mass of an atom. So if I give you the atomic mass, this number might have some decimal points because it's experimentally determined. And what I say to kids, for this one is this basically happens in fancy, shiny lab equipment that costs a lot of money. Okay, we don't have that equipment here at Legend High School, so we are not in this class going to experimentally determine the mass of a single atom in this class. Usually we're using some high-tech lab equipment to really get as accurate and precise as possible with this. So this is something that will be given to you in a problem. Okay, next we have the average atomic mass, right? You see why this causes a headache? Mass number, atomic mass, average atomic mass. This is a calculated mass, and it's based off the weighted average. Of all isotopes. So I am going to teach you today how to calculate the average atomic mass. You can do this. This guy will also have decimals, and notice this AMU. That's going to be our unit for average atomic mass. Well, what is AMU? That's this guy right here. Atomic mass unit stands for AMU stands for atomic mass unit. And this is the unit we will use to describe how much mass an atom, molecule, subatomic particle has. It's the number that you see on your periodic table, right? That's what these guys are right here. So this guy is the P table. This guy is lab. This guy is protons plus neutrons. All right? All right, so calculating average atomic mass. Let's get into figuring these out. This is, remember, the one that's calculated on the periodic table. So first thing we're going to do is we're going to take the percent abundance of each isotope and convert it to a decimal. So we got to divide that percent by 100. Then we're going to multiply the decimal, which is now called the relative abundance, if you want to know what that's called, by the atomic mass of each isotope. And then we're going to add up each result of number 2 from step 2, add up each result, and that will give us the average atomic mass, which has a unit AMU. One thing I would like to just throw in, if we do not have the atomic mass, remember that's the one that's calculated in a high-tech lab. If we don't have that, so if no atomic mass given in the problem, then we're going to do mass number. That's the next best option. Okay, here's a typical problem, and I know this might cause a little stress for you that don't like math or don't like word problems. So we're going to just try to read this once. That's my goal. All right? Don't tell your English teachers that I only want you to read this once, because I'm pretty sure they would love it if you read everything they gave you 6 times. But my goal is to only read this once, because I find that if I keep going back to these problems, I accidentally take the wrong numbers because a lot of stuff sounds the same. So I make a table, and I fill out the table as I read. You don't have to do it this way. You can look up other videos, and teachers do it lots of different ways. But I find with my ADD brain This table helps me only have to read a word problem once, and reading a word problem once is already more than I want to read it. Okay, so it says copper has 2 naturally occurring isotopes, so we're going to have 2 isotopes. One is copper 63 and then copper 65, so I'm going to put those under isotope, and I put the full name, copper 63 and copper 65. So I took care of that. The percent abundance of copper 63 is 69.17%. So I'm going to put that down right now. Percent is 69.17. Check. The atomic mass, so that's the fancy, shiny, expensive lab equipment one, of copper 63 is 62.94 AMU. So that means they're giving us atomic masses. I don't need mass number. So if we have atomic masses, that's the one with the decimal. With the AMU, we're going to use that instead of mass number. So we have 62.94 AMU. The percent abundance of copper 65, so now we're on the second isotope, is 30.83%. So we took care of that. Its atomic mass is 64.93 AMU. Calculate the average atomic mass for your copper. All right, so I made this table. Now I don't have to go and look at those numbers in the word problem ever again. So step 1 is we take our percent abundance and we divide it by 100 to make it a decimal. Or, for those of you who like to do things in your head, you just move the decimal 2 spots over. So either divide by 100 or move that decimal 2 spots over. Step 2 says we are going to multiply that new relative abundance, which is this guy. We're going to multiply that by the mass for that isotope. So I'm going to multiply this times this guy. And when I do that, I get 43.53. And I'm going to do the same thing down here, multiply this one by this guy, and I get 20.02. And the last step then is we take this piece and this piece, so each isotope, and we add them together. So when I take 43.53 plus 20.02, I get 63.55, and the unit is AMU, atomic mass unit. Okay, before we are donezo, I need you to take out your periodic table, find CU, it's atomic number 29, and I need you to see, does this answer make sense? Look at the average atomic mass on the periodic table for copper. Is 63.55 close? Absolutely, it's close, so our answer makes sense. And when I say close, I mean off by maybe a couple decimal places. If I got 20 as my answer or 90 as my answer, I would be concerned. So we are in good shape. This answer makes sense. We are good to go. All right, one more problem together, and then I'll let you fly solo. So it says 70% of all nickel atoms have 28 protons and 30 neutrons. Oh, geez, so they are making me do some work. So here's what I see, 28 protons and 30 neutrons. Well, I don't care how many protons there are. I already know nickel always has 28 protons, but what I do care about is the mass number. And remember, protons plus neutrons equals my mass number. So 70% of all nickel have 28 protons and 30 neutrons. Well, 28 plus 30 will give me this mass number, which is 58. So that's kind of rude of them. They're making me do more work before I even get to the actual problem. Okay, 30%, right? These should always add up to 100%. Have 28 protons and 31 neutrons. So it's still nickel because it has 28. But now my mass number is 59 because 28 plus 31 is 59. And then we want the average atomic mass of nickel. Okay, well, we're running into a problem here. Did they give me this fancy experimentally determined AMU mass number? Or excuse me, atomic mass? No. So we don't have that. The next best thing, the only thing available is the mass number, which is this guy here. So I'm just going to copy those over, 58, 59. Again, we don't do that unless they don't give us atomic mass. Okay, that's our next best option. So step 1, I know it's kind of hard to believe we're only on step 1 once we have to do all this work ahead of time, but we are ready to roll. So step 1, divide by 100, 0.700, divide by 100, 0.300. Multiply. So 0.7 times 58 gives me 40.6. Multiply. 0.3 times 59 gives me 17.7. Add those bad boys up, I get 58.30 AMU. Is this answer closer to nickel 58 or nickel 59? Well, if we were right smack dab in the middle, our average would be 58.5, right? That's halfway between 58 and 59, would be 58.5. Why do you think this answer, 58.3, is closer to nickel 58 instead of nickel 59? Well, look, the percent abundance. Most of the time, like if I have 100 nickel atoms and I randomly draw one, 7 out of 10 times, okay, or 70 out of 100 times, I'm going to get nickel 58. That should count more towards the mass, right? The mass should be closer to nickel 58 because more atoms are of nickel 58. That's what percent abundance is. It's telling me if I had 100, 70 of them would be nickel 58, 30 would be nickel 59. So the average mass is a weighted average. That's why we do it this way, okay, instead of just adding the two together, because we know nickel 58 occurs more often, so the overall average should be more like nickel 58 instead of nickel 59. Okay, this one's a little tougher because there are 3, oxygen 16, oxygen 17, and oxygen 18, but I want you to pause the video for real and try this guy on your own. All right, here's everything worked out. I will say that what I notice is because oxygen 16 exists so much more often, right? Let's get my little highlighter. 99.6% of the time. Just be careful. These percentages look really small already, but we still have to divide them by 100. So look at how tiny these two guys are. So just be careful. Really make sure you're dividing by 100, and if you're not confident moving the decimal 2 spots in your head, just to use your calculator, divide by 100. Okay, we multiplied and then we added up all 3 pieces this time, got 15.998. Let's monitor for meaning real quick. Look at your periodic table. What does it say for oxygen? Hopefully it says 16.00, or if you're looking at the one on the wall, 15.998. So good work. All right, last one, I got to end with a little twist, of course. This one, element X. I got news for you people. There is no element X on the periodic table. You need to tell me what element this is. Well, if we're checking our answers right now with the periodic table, my hint for you is maybe we could solve for the average atomic mass and use that to try to identify the element, how we normally check, right? So find the average atomic mass and then see what element has the closest average atomic mass. So pause your video, give this last one a shot. Woohoo! I got 10.80 atomic mass units, AMU, and on the periodic table, that average atomic mass is closer to boron. So element X is boron, and they did say what's the atomic number. Boron has the atomic number 5. Good job, guys. I know we don't love crunching numbers, but I'm proud of you, and we'll practice a lot in class.